Kevin?
Yes, dear?
What the heck is an R-2R ladder?
Oh, Lord, didn't I explain that yet on the channel? Hi, I'm Kevin. Welcome to my cave. Recently, I was showing you all a circuit that was testing out our op-amp peak detector. And I mentioned that I was converting the output of a 4-bit counter from digital to analog using an R-2R ladder. Mrs. Kevin helpfully pointed out that I'd never explained what an R-2R ladder is. And I realized she was right. That was because the only time I've shown the innards of a D to A converter was in the episode on the op-amp adder. There, I was using a direct conversion technique. The input bits were wired into a virtual ground through individual resistors, with each value being twice the value of the previous one. For the 8-bit example, the values ranged from 3,750 ohms, which we got from two 7.5K resistors in parallel, up to 480K ohms, which we got from two 240K resistors in series. This technique is not popular for very good reasons. I used it in the demonstration only to have an extreme example of a summing amp. The reason is that it doesn't scale. This 8-bit converter is near to the practical limit. If we look at the resistor that we used for the most significant bit, we'll see that if we're using 5-volt logic, that resistor will be carrying a current of 5 volts divided by 3,750 ohms, 1 1/3 milliamps. A CMOS logic gate can't source more than a couple of milliamps off of a 5-volt supply, so we're close to the limit at this end. And at the other end, we don't want to go more than a handful of megohms, because we start getting into the territory of low noise and very high impedance circuits, and we saw last time in the peak detector what a pain it can be to get those right. But there are very common 16-bit D to A converters out there. They're not even that expensive, $4 or so in hobbyist quantities. And there are even ones that purport to be 24 and 32 bits. They're only a little pricier. Maybe $13 or so if you can't solder a ball grid array. If a 32-bit direct DAC used a 2.5K resistor on the most significant bit to limit the input current to 2 milliamps, it would need a 5.37 tera-ohm resistor on the least significant bit to get the right current balance. Clearly, that's not going to work. So how the heck do these converters do that? Well, one of the simplest ways is a circuit called an R-2R ladder, because all of the resistors are either a given value R or twice that value, 2R. Let's see how one is constructed. Before we continue, let me interrupt for a few moments. My videos are always free to all comers. Nothing is ever paywalled, and I don't waste your time selling various dodgy products. But I do end every video with a plea that you take care of one another. To this end, all the channel's ad revenue has gone to charity. This month's featured recipient is Médecins Sans Frontières, Doctors Without Borders. MSF is an independent international organization that offers medical humanitarian aid to people based solely on need, without regard to race, religion, gender, or political affiliation. It provides over 10 million consultations annually in more than 70 countries, including some of the regions most torn by violence, neglect, or catastrophe. And it trains health workers and invests in local infrastructure to meet healthcare needs sustainably in a community-driven way. I'm asking my viewers to join me in supporting this organization. This is a small channel, so I've set a modest goal of $500. Those $500 could provide 2 treatments to cure patients of hepatitis C, 4 resuscitators for non-invasive ventilation in newborns, or enough vaccine to immunize nearly 1,400 children against measles during a deadly outbreak. We managed to meet our goal in the last fundraiser, so I'm sure that my wonderful viewers can get us there again. Won't you please join me today? Thank you so very much. We'll start with a 0-bit DAC. What's a 0-bit DAC? Well, with no input, all it can output is ground. Pretty trivial, I know. Now, how could we make that into a 1-bit DAC? Well, we can put a resistor in series with it, and another resistor in parallel up to the first input. That input will be a logic high, that is, some voltage V, or a logic low, that is, ground. I'll call it B1 times V because B1 will turn out to be the 1 bit of a binary number. The two resistors will each be a value 2R. Let me keep track separately of what the Thevenin equivalent circuit is, as I continue to add parts. Right now, it's a simple voltage divider. The output voltage will be half the input voltage, and the Thevenin equivalent resistance will be just R. I'd like that to be 2R. That's easy enough. Put in another resistor in series whose value is R. That'll give us a Thevenin equivalent of half the bit 1 input voltage through a resistor of 2R. This circuit now looks like what we started with, a constant voltage through a resistor of 2R. Since it looks like what we started with, we can play the same game again. Add a parallel resistor up to the 2-bit. That'll make our Thevenin equivalent into a voltage divider again. The output voltage will be the average of the 2-bit voltage and the voltage from the first stage. And we can simplify the expression. Once again, our equivalent resistance is just R. We want it once again to be 2R, so we add another series resistor. Now we have a 2-bit output with an equivalent resistance of 2R. Can you see where this is going? We can add another pair of resistors for the 4-bit. I won't show the algebra, but the voltage divider winds up doing the same thing, and now we have a 3-bit DAC. And we can carry out this process for as long as we please. Another stage makes a 4-bit DAC, and so on. The R-2R configuration uses twice as many resistors, but resistors are cheap. It needs only 2 values of resistor, and in fact it needs only 1, since you can use pairs of resistors in series or parallel to get the other. It's what I used in the tester for the peak detector, and you can see it here. Resistors of only 2 values, hooked up as a chain of voltage dividers. You can use resistors with tighter tolerances if you have the budget. There are resistor arrays made that have matching ratios of 100 parts per million or better, for a price. Or you can simply use a packaged commercial D/A and let your vendor worry about it. This isn't the last word on D/A converters by any means. But rather than get immediately into other ways of doing the conversion, let me get into some of the pitfalls that you're likely to encounter. We've already seen the two that I want to discuss. The first is nonlinearity and even nonmonotonicity. A bigger number can sometimes give a smaller output voltage. We see this in the middle of the trace that we got from the direct DAC. There's really no fix for this other than using better matched resistor values. I was just using 1% resistors picked out of a box, so having a jump of about 1% of the full-scale value is just expected. If you use a commercial DAC, the datasheet will specify what nonlinearity you might expect. A worse problem is the glitches that appear in the transitions. You can see in this trace they're pretty bad. The cause of this is a pathology that the engineers call clock skew. The input bits aren't all changing at the same time, and so the output values can swing wildly while the circuit is seeing some changed bits and some unchanged ones. The counter that's driving this circuit is the big culprit here. It's of a type that's called a ripple counter. A ripple counter gets its name because when it counts, the bits that change ripple up from the least significant bit to the most significant one. Let's see what happens when we start from a count of all zeros. We'll advance to a count of 1. A single bit changed, so there should be no glitch, and that's what we see in the scope trace. But now when we advance the count to 2, the counter very quickly visits 0 before advancing to 2. That turns up as a downward-pointing glitch in the trace. At this horizontal scale, the scope isn't fast enough to show it falling all the way to 0. Advance the counter to 3, and again only the single least significant bit changes, no glitch. But when we advance to 4, the counter output briefly visits 2 and then 0 before settling on 4. That means that the glitch is 3 times as deep and lasts twice as long. It shows up as a bigger spike on the scope. When we go from 5 to 6, the counter visits only 4 as an intermediate value. So we get a relatively small glitch again. Advancing from 7 to 8, the counter visits 6, 4, and 0 as intermediate values. 3 intermediate states and a dip all the way to 0 give us our worst glitch yet. And the pattern of glitches continues for the rest of the cycle. At the end of the cycle, there are 3 intermediate values again, but each one is less than the last, so the reset to 0 looks as if it's just a slow transition. When we look at the output from the 8-bit direct DAC, we see it's a forest of spikes. They point to the other way from the previous example because the direct DAC is an inverting configuration. There are also spikes going in the opposite direction. I suspect that even the scope cable and downstream circuitry presented too much of a capacitive load, and the sudden changes are making the output overshoot and perhaps oscillate. I suspect that I could have fixed that problem by adding some additional compensation to the feedback loop. By now we've seen that a bunch of times. But I didn't bother for the second video in this series. It would have just caused confusion. So what could we have done about all the spikes? Well, one answer is to make all the input bits change at the same time, possibly by holding them in an array of latches with a common clock. For this simple ramp generator, we could have gotten the same effect by using a synchronous counter, like a pair of 74HC161s. But there are a bunch of commercial D to A converters that offer latched inputs. In fact, a lot of modern ones need to latch their inputs because they interface to a microcontroller using a serial interface like I2C or SPI. Another approach is to follow the DAC with a circuit called a sample and hold. It can take an analog signal at a given point in time and present it to its output, or else hold the output constant while the input continues to vary. But that's the topic of the next video, and I hope you'll stay tuned for that. If only you had some way to tell the YouTube algorithm that you want to see it. In the meantime, stay safe, stay healthy, stay curious, and take care of one another. Bye!